Hello and welcome to the Bresenham Line computer graphics practice video. And in this week, in those tasks, we'll be dealing with the topic of rasterization. So rasterization is when we have some shapes that we want to display on the screen, but because the screen is a grid of pixels, we need to know which pixels we need to color and which we do not. Which pixels will be inside the shape or representing the shape, and which are outside the shape and we don't care about. So we'll be in the first task, in this task we'll be drawing lines. So line drawing is very important in the sense that for example, if you look at this text that's is on the screen, this text is made out of lines. Of course, there are also curves and different other shapes, but lines are in some way like the most simple of those shapes. So we'll be trying to draw those. Of course, also if you think about this, then all of this text is actually drawn very fast. So this algorithm or different rasterization algorithms often need to be extremely fast. Millions of times in a second, different lines will be drawn on one screen. So Bresenham Line. There are also other algorithms that use like similar approaches. We will see the Bresenham triangle, but there's also a circle drawing algorithm and so on. But the Bresenham Line algorithm is quite simple. Let's see how the Bresenham Line algorithm actually works. So assuming we have a line we want to draw from this pixel to that pixel. So, and we assume that the center of the pixel is at its coordinates. For example, if we have coordinates 1, 2, 3, 4, and 1, 2 in that axis, then this start of the line, this point here, is at coordinates 1, 1. And now you can envision that the line you want to draw is probably something like this here, but you don't know yet which pixels to color. Now, because the line is starting at this pixel, then this one you definitely want to color because it's the starting point of the line. But for the next pixels, the Bresenham Line algorithm works like this, that we take one of the axes, the one where the change of the line is higher, and we take a step in that axis. So it's an iterative process. So we step from x coordinate 1 to x coordinate 2. Now on that step, the line will deviate from the center of the pixel, right? And we need to find out how much this line deviates. So for that, we need to know the slope of the line. So currently, we can see that it moves from coordinate 1 to coordinate 4, so the change in the x direction is 3, and it moves from y coordinate 1 to y coordinate 2, so the change in y direction is 1, meaning that the slope here is 1/3. If we move 1 unit in x, we move 1/3 unit in y. So at that point, we need to kind of accumulate this error, or this accumulated error. This is the core idea of the algorithm, that at each step we check how much have you deviated from the center pixel of the current line. Now in that step, we just add this slope to the error. So initially it's 0, but when we have moved here, it will be 1/3. And we have to check if this error is greater than 1/2. So 1/3 greater than 1/2, it is not. And this means that we don't move to another coordinate in the other axis, but we stay on the same row currently. And we color this pixel. Now we keep continuing this and we take another step and now add the slope to the error and we get 2/3. And what happens now is that 2/3 is larger than 1/2. Our line has actually crossed the border between those two coordinates. What we want to do now is we want to move one unit to the other row because of this condition. And in order to do that, well, first we do it, but afterwards we also need to subtract 1 from the error, because now we will be measuring error from this point. And we color the new row. We just checked that the error grew larger than 1/2. We moved to another row and we want to do 2/3 minus 1. This is negative 1/3, and this is exactly the distance from the line to the new center point on the new row. And then we continue. Now our new error is minus 1/3, not 2/3 anymore, and we take the step, we add 1/3 to it, we get back to 0, and this makes sense because the last endpoint is also at the center of this pixel. And we color the last endpoint. And this is pretty much the whole algorithm. Of course, your slope may be different, you need to calculate it. And all you do is you add this slope to this accumulated error. If it's big enough, you move to another line and subtract 1 and keep continuing this process. Now, what you want to check additionally is that which way is the error actually increasing, in the sense that currently our error grows because the line is ascending. If it were descending, then the error would actually go negative. This means that for each unit we move in x-axis, the y-coordinate decreases. And then we need to check if our error is less than minus 1/2. So if it's less than minus 1/2, then we move to a lesser row or another row on the y-axis. And additionally, you need to check which is the axis you're going to iterate over. So currently here we chose x because the error or the slope in this way was less than 1. If it would be greater, then your line would be something going here, and in that case you don't want to use that axis but the other one. You want to do the steps on that axis, and then at each step check if you need to move to that column of pixels or not. And this is pretty much the algorithm. Just check if it's a steep line, so that line would be steep, or a non-steep line, and check if it's ascending or descending, and you can rasterize any line you come across with this algorithm by just iterating over one of the axes and keeping track of the error and moving on the other axis when the error is big enough. Now we can look at this in code as well. So if you download this file and open it up, you should see something like this. Now we can also open it here. So you can see that already some lines are being drawn. This thing on the left here is from the canvas drawing functions, and this thing on the right will be what your Bresenham Line rasterization algorithm will draw. This is just for comparison. This one also uses some anti-aliasing techniques and so on. So let's look at the code. In the code there is this context and Bresenham context. So the left context is that one, and the Bresenham context is the one where you are drawing onto with your algorithm. This is just some place where there are different lines generated, and then we loop over the lines, call the draw line, which is your begin path, move to line to stroke that we have seen before. And next we have this Bresenham line, which is quite a big branching algorithm. Now it is this way because, like I mentioned before, this algorithm needs to be quite fast, and if we can only use like a few ifs rather than some more complicated mathematical operations, which would lessen the number of lines in the code, but would increase the decrease the performance, then we would want to use the branching structure instead. So also implementing it like this will help you understand the algorithm better. There are different algorithms like on Wikipedia and so on that you can of course look at and study, but the idea is that if you implement those, then you could measure the speed of those with the speed of this one, and this one might turn out to be faster. Of course, in JavaScript it's kind of, they're both really slow. In that sense, you don't want to use this thing in JavaScript. Like there just isn't enough performance here. But if you're implementing it on some lower level, then this performance is noticeable. Even if it's like a fraction of running this algorithm once, if it's run like some million times per frame, then this fraction is a really noticeable amount. Okay, but what we have here is we are measuring this delta, so change in x. Just take one of the x coordinates and subtract the other x coordinate. Change in y, we take the y coordinates, and we can check that if the change in x is greater than the change in y, then we have a non-steep line. So this means that if you remember here, the change in x is greater than the change in y, so 3 is greater than 1, it's a non-steep line. With this line, our change in x would be 1 and change in y would be 2, so it doesn't satisfy the condition, that would be a steep line, and we would need to iterate over the other axis. But here we have a non-steep line branch. So in the else case, we have a steep line branch. So here we find the slope, so I've called it the change in error. So each time you move a pixel in the x-axis, then this will be how much your error needs to change. And yeah, now we need to check if it's an ascending line or a descending line. So if this error is less than 0, then it's an ascending line. And this is a bit contrary to what I've written here. So here it's positive and it's an ascending line. But if you look at the coordinate system of the canvas, and if you remember, it was like 0 was here and the axis was this way. So the y-axis, the positive direction is down. This is why a negative slope actually means an ascending line. So the slope here is negative because the y will decrease, but visually it's ascending. So in that place we need to check if the error is less than minus 0.5. So here we just assign the current y, so where we are on the y-axis, and we will start iterating over the x-axis one at a time, just like we did on the whiteboard. Then we draw a pixel, we add the error, so this change we found that each step produces, we add it to this accumulative error. If this error now becomes less than minus half, then we need to move 1 unit up on the y-axis. So up meaning visually up, negative on the actual axis. And we increase the error by 1 because we have moved 1 unit. And this will draw ascending non-steep lines. Exactly those that you can see here. They're ascending visually and they're non-steep. And now what the task is, you need to fill out this branch and create 2 branches in this steep line branch as well. So there will be 4 branches: non-steep ascending, non-steep descending, steep ascending, and steep descending. And we can try to do this one branch here, so it's quite similar to what we're doing here, pretty much the same, but we want to see if the error is now greater than a half. If it is, we want to add y, and we need to subtract 1 from there. And let's see if that worked. And we have descending non-steep lines. And similar things you need to do with the steep lines. Of course, in the steep line case, you iterate over y and increase the x if needed. Now, if this should be greater or greater than equal, this doesn't really matter much. It's 1 pixel somewhere, maybe at some times, so don't worry about this. Just make sure you're consistent, and that's it. Now you might be interested by this putPixel function. So this is just, it draws a filled rectangle, and it uses RGB. Color has the style. I recommend you to check this out, because you could do it like this, but it's really slow. And on this site you can actually performance test different algorithms. And for example here, setting HTML5 canvas pixel, there are 3 ways how you could do it. I'm gonna check if okay, I'm at revision 1 currently, so there are 49 different revisions people have created. I'm gonna just take this revision, and here, if you run tests, then those codes will be run on your browser. It's currently running, and times will be measured, and you can see how fast is one algorithm or one way of doing the same thing compared to another. And there are also, after this is run, it shows you the speeds of different, the results of, from different people as well. What you can also notice here is that this currently the fastest algorithm that's here is only become fastest in the latest Chrome version. So this 49. A couple of versions back it was quite slow compared to, for example, this filrect with Global Alpha. But here, this filrect with Global Alpha, it's still faster than a regular filrect, because with this filrect you have this additional concatenation, additional conversion here. With Global Alpha, for example, you don't concatenate those values, so it's this one concatenation might save you some time if you're really if performance is really something you're after. and it's useful to like see how Chrome has optimized some of their things so that some algorithms become faster, others might become slower. For example, this thing in the 46 version it was quite fast. In the 47 for some reason it dropped down. So things change, and it's cool to find this out. So currently it seems that this algorithm is about twice as faster than this one, so you might want to use that one as your boot pixel instead. So it kind of depends on browsers and what are you actually wanting to do. Okay. Yeah, so that's about this task. Should be relatively simple. Just make sure you understand the algorithm and have considered those different values in a correct way in all of the branches. Okay.